Hi, in this set of podcasts, we're going to look at something called chirality, a different kind of stereoisomerism. Now, if I hold up a pair of scissors like this, I'm right-handed. I know that when I hold it, it feels right in my right hand, and I can cut it just fine. Now, if I were a lefty, I'd hold it and it wouldn't feel right and it wouldn't cut very well. So this pair of scissors has handedness. So if I hold up a pen like this, a right-handed person can write with it just as easily as a left-handed person. So this pen doesn't have a handedness. Now, what's the difference between these two objects? Well, let's look at a couple more objects and see if we can figure out the difference. Every single key on this ring has a kind of handedness. Now, if you look at all of these keys, the top side is different than the bottom side. So you can't cut it in half and have a mirror image because these sides are different. And in fact, the little ring that holds all the keys also is in a spiral. It starts out as a top here and it ends as a top down here. Now, if you look at every single thing in my hand right now, none of them have a plane of symmetry. So anything that has handedness doesn't have a plane of symmetry. So if we look back at the pair of scissors, there's no plane of symmetry down the middle or down the side. You can't cut it in half and it won't look the same on either sides. But if we look at the pen and we cut the pen in half this way, the left-hand side is exactly the same as the right-hand side. So that's why the pen doesn't have a handedness. Now, of course, your hands have handedness. If I hold them like this and I line up the tops with the bottoms, the thumb and the pinky don't line up. If I line up the thumb and the pinky, the tops and the bottoms don't line up. Now, why is this so important? Well, just like your hands don't have a plane of symmetry, there are molecules that don't have planes of symmetry. Okay, let's look at a couple of molecules. This molecule right here, they're all sp3 carbons, and don't worry about what the substituents are. Just let's look at the colors. If we look at this molecule right here, it has two of the same things attached to the carbon. And so if you want to find the plane of symmetry, it's not through here. It's right through here. So if you cut this molecule in half like this, it has a plane of symmetry. So it really doesn't have a handedness. Whereas if you look at this molecule with four different things attached to the sp3 carbon, there's no way we can find a way to cut it in any way that would have a plane of symmetry. Because of that, I have another molecule here, same four things attached. But now if you look, these two are mirror images of each other. When I hold them up like this, it looks like there's a mirror right between them. Now, they both have handedness and they're mirror images of each other. But because they don't have a plane of symmetry, mirror images can never fully line up, just like our hands can't line up. I can line up the white and the blue balls, and then the red and the green balls don't line up. Or I can line up let's try this. Let's try the green and the blue, and then the white and the red don't line up. So these molecules are non-superimposable, but they are mirror images. So this is a kind of handedness that we'll be talking about in molecules. Now, why is this important? Well, molecules interact with things that are chiral differently. So this molecule will interact with a chiral thing, like an enzyme, differently than this one. So whenever you make a molecule that someone's going to use, especially drug manufacturers who make molecules that will be used by enzymes in bodies, they have to understand the handedness of the molecules.